Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. Water is the most amazing and special substance on this planet. Our bodies are mostly made up of water. Water covers over 70% of the surface of this planet in forms of oceans, seas, lakes, rivers. Water is fundamental in industry because it's such a great solvent and coolant. And all these amazing and other amazing properties of water really boil down to unique physical-chemical property of water, and that's hydrogen bond. And that's what I will discuss in great detail in today's video. All these special features of water, such as water having high heat capacity, probably the highest heat capacity of all naturally occurring substances on this planet. Fact that the solid of water, namely ice, floats on liquid water is not typical of materials and substances. Usually it's the other way around, namely solids sink in the liquid. Then water having very high surface tension is also a peculiar phenomenon. Some insects can walk on water. Water is also, as I said, excellent solvent, particularly for salts. And all these boil down to hydrogen bond. So let's explain how and why this hydrogen bond results in these unique properties of water. Chemical formula of water is H2O. 2 hydrogen atoms and 1 oxygen atom. And how these atoms are arranged in a molecule makes all the difference. For example, if this is an oxygen atom, then if these 2 hydrogen atoms were arranged like this, then this would be a linear arrangement and water would not have all these amazing properties that it does, and it would not have that specific hydrogen bonding that we talked about. So this is not how a water molecule looks like. Instead, a water molecule looks something like this. If this is an oxygen atom, which is effectively larger than hydrogen atom, then 2 hydrogen atoms are forming the so-called Mickey Mouse shape, like 2 ears and head. And the angle that these hydrogen atoms are making is very important as well, and it has value of 104.5 degrees. Now let's discuss a little bit this arrangement, and let's discuss how this molecule is formed from these 3 atoms. As we know, hydrogen is the first element in periodic chart, and it has 1 electron. Now oxygen has atomic number 16, and because it has 8 protons and 8 neutrons in the core, 8 and 8, 16. So that means it also has to have in total 8 electrons. But it has 2 orbits. This is now very important. So out of these 8 electrons, 2 electrons are in the inner orbit close to the core, and 6 electrons are in the outer orbit. I already discussed this in one of my previous videos, I think. This is the so-called valence orbit. So these electrons in the outer orbit indeed can be used in chemical bonds because it's in complete orbit. It would like to have 8 electrons in the outer orbit. So it can use these electrons in covalent bonding. And that is what is happening when water molecule is formed in a following way. You see, let's take this hydrogen atom. This hydrogen atom will donate its only electron, and it will take one of these 6 electrons in the outer orbit to form this chemical bond. We call that covalent chemical bond between this oxygen and this hydrogen. Now, this hydrogen will donate its only electron, and this oxygen will give another electron from these 6 in the outer shell to make this covalent bond between this hydrogen and this oxygen over here. Now, out of 6 electrons in the outer orbit, 2 will be used for this covalent bonding. 6 minus 2 is 4. So that means that the outer shell of this oxygen will have what we call 2 pairs of lone electrons, 2 pairs, 6 electrons that will be unused in this oxygen. Now, as you can see, this molecule is electroneutral. It's not positively or negatively charged. However, oxygen is electronegative. This is another property. I will not go into depths, although this is already a technical video, despite the fact this is fundamental playlist, but the nature of the lecture is such that I have to be more technical than in other fundamental videos. But I could be even more technical and quantitative, which I will avoid in this video. But anyways, oxygen is electronegative. That means it has affinity towards electrons much more than hydrogen in this case. The reasons are technical, but in very simple words and some simplifications, I can say it in the following way. The core of oxygen is very large relative to the electron orbits compared to some other atoms. So, and core is positively charged. Because that core is large compared to the orbits, I mean, it's still smaller than orbits, but it's large compared to some other atoms, it means it attracts these electrons very much. And that means that because it's electronegative, the oxygen part of the atom is negatively charged. This part over here is negatively charged. And consequently, because this is electrical induction, if this is negatively charged, consequently this hydrogen side of the molecule is positively charged. So you can see that the molecule of a water forms these 2 poles. And we call this configuration dipole, negative pole and positive pole. And this dipole nature also means that this whole molecule is behaving like a small tiny magnet that has positive pole and negative pole. How is this related to hydrogen bond? What I'm about to say is the key statement. Hydrogen bond is not connection, link, bond between these atoms that are making water molecule. Hydrogen bond is intermolecular force between water molecules. Because this is positively charged, this is negatively charged, and maybe somewhere here there will be another water molecule with these hydrogen and this oxygen atom, and this one is positively charged part, this is negatively charged part. Well, this positive and this negative will attract. And this attraction between positive and negative poles of different molecules is hydrogen bond. And that attraction results in all or most of these unique properties of water that I'm about to discuss in the rest of this video. So when you add together trillions and trillions of molecules of water in a glass of water or any other body of water, all of them behaving like tiny magnets that are attracting and repelling each other, then that results in properties such as surface tension, such as high heat capacity, such as the fact that ice floats on liquid water, and so on. So let's discuss how this hydrogen bond, unique bond for water molecules, results in these unique properties of water. Why ice floats on water? Well, that has to do with the thermal jiggling of molecules and hydrogen bond. Namely, when we have temperatures above 0 degrees Celsius, then 2 molecules of water perhaps would like to come together and form a hydrogen bond, but there is thermal jiggling that is stronger than that attractive force of hydrogen bonding. As the temperature is decreasing, that thermal jiggling is weaker and weaker, still exists, but at 0 degrees Celsius, that thermal jiggling is now weaker forcing than hydrogen bonding. And these molecules can lock together, forming a crystalline structure of ice. Let's examine that crystalline structure of ice, and then it will be clear why ice floats on water. So if we start here with one molecule of water, I will use black to indicate oxygen and red to indicate hydrogen. So this is oxygen, and then we have this hydrogen over here and another hydrogen over here, forming Mickey Mouse, angle 104.5 degrees. Now, with blue, I will indicate hydrogen bond. Hydrogen bond between this molecule and another molecule, perhaps here, that will have oxygen over here, and it will have its own two hydrogen atoms, one being here and another Mickey Mouse being here, Mickey Mouse ear. Again, 104.5 degrees. Now, there is another hydrogen bond between this hydrogen and another oxygen atom here. And this oxygen atom in turn will have hydrogen, hydrogen, forming Mickey Mouse 104.5 degrees angle. Now we continue. This hydrogen will form a this hydrogen will form a hydrogen bond with another oxygen atom of a water molecule, and this oxygen atom will have two hydrogen atoms connected at an angle 104.5 degrees, forming Mickey Mouse shape. Now you see where I'm going. This hydrogen will connect with another water molecule where we will have oxygen over here and two hydrogens, one hydrogen over here, another hydrogen over here. And finally, you can see now that this hydrogen will bond with another oxygen over here. And this oxygen will have one hydrogen attached here, another hydrogen attached here, again 104.5 degrees. And the picture is completed because this hydrogen will now bond through hydrogen bonding with this oxygen. And look, we have 1, 2, 3, 4, 5, 6. 6 water molecules forming ice. Now, it's important to reiterate what I said at the beginning. This arrangement is possible because thermal jiggling of these molecules, let's indicate here, there is thermal jiggling of this molecule left-right, but that thermal jiggling is weaker than this blue hydrogen bond. So the crystal is jiggling but in place. When temperatures are higher, then this jiggling is stronger than the blue bonds, hydrogen bonds, and water is flowing around. The fact that the water at higher temperature is flowing around means that this jiggling on average brings water molecules closer together than what the distance is when they form this what we call crystalline structure. So in ice, key sentence, in ice, average distance between water molecules that are locked in this hexagonal shape is larger than the average distance between water molecules in liquid state. And consequently, density of ice is smaller than density of water. Because the average distance of molecules in ice is larger. And that's why water expands as it cools, expands to satisfy this requirement of larger distance between molecules. And because density of ice is smaller for this reason than density of water, ice floats on water. They say this is also the reason you slip when you step on ice. Because you see, when I stand on this floor, this is solid state of some material. And that material is just satisfied to be compressed, because solid state is usually denser than liquid state. So when I step on this material, it's just fine with being compressed. But when you step on ice, ice expands as water freezes. And when you step on ice, you try to undo that expansion. And that creates a little bit of thermal effect that melts the surface layer of ice, forming water, and you start slipping. Because, again, of this property that ice is less dense than water. So the lakes, for example, will freeze from top to bottom, rather bottom than top. And the fact there is a layer of ice on top allows fish and other marine life and plants to survive under the sheet of ice, which would not be the case if you have freezing from the bottom and there is no ground anymore. There is no soil at the bottom, it's just solid ice. Now we can move on explaining another fascinating property of water. How does one explain high surface tension of water? Because you saw many videos in which some insects can walk on the surface of the water. I also had video in which I managed to put a needle on the surface of the water and it stayed. But yet, a person cannot walk on the surface of the water, you will sink. So how is that possible? How is it that these small objects can float on the surface of the water, yet bigger, heavier objects cannot? Well, that also has to do with the surface tension and hydrogen bond. So if this is the surface of the water, and let's say this is air and this is water, H2O, then what is the arrangement of molecules in this liquid water? Well, if we have our oxygen over here, and it has hydrogen over here, and another hydrogen over here, angle 104.5 degrees, and then we have hydrogen bond between this hydrogen and another oxygen, and this oxygen has its own hydrogen like so, and another hydrogen like so, again angle 104.5 degrees. Now this hydrogen bonds with another oxygen, and this oxygen also forms a hydrogen bond with another hydrogen and so on. So you can see that there is this formation of water molecules at the surface in a way that there is hydrogen bond keeping them together in this horizontal plane, and this hydrogen bond is like a stretchable membrane. If you pull them apart, imagine you take these two molecules of water, you pull them apart, this hydrogen bond will tend to bring them back. Now, there is more molecules of water, and of course some of them are deeper, not in this surface layer. So if I take oxygen atom over here, then this oxygen atom will have its own hydrogen atoms to form water, like so. Again, angle 104.5 degrees. But notice that there will be also a hydrogen bond, like so. This oxygen will be attracted to this hydrogen as well as this hydrogen through hydrogen bond. And there is another oxygen over here that forms water molecule with two hydrogens, and it will also form a hydrogen bond with this hydrogen, and there will be with some other over there, and so on. You get the point. So you can see that this hydrogen will be attracted, if you wish, with these two to these two molecules of water. In other words, there will be an attractive force in this direction as well as in this direction. Well, in this direction and this direction means that there will be overall a component of the force down, because I can decompose this into horizontal direction and this vertical direction, green being vertical direction. So you can see that this molecule through these hydrogen bonds is pulled down. Well, the same happens for this one, because this one will have another hydrogen bond with another molecule. So, key sentence is the following. While these molecules in the interior of water will be on average pulled equally in every direction through these hydrogen bonds, molecules at the surface will be pulled more towards the interior of the water than up or on the side. Why? Because here is air. There is no another water molecule to counterbalance this green force. So each of these molecules would like, if you like, to go into interior of water. So if you have this surface of the water and each of these molecules wants to go in, what that will result is that the free surface of the water will not be flat, but it will rather be a sphere, because each of them wants to go in, and that is only possible if they form a sphere in the absence of some external forcing that prevents it, like when you put water in glass. That external forcing is the container of the glass. So hydrogen bonding that you see here is responsible for this spherical shape of drops in free state. How is this, however, related to surface tension? In other words, if we put an object over here, an insect, why is that insect not sinking, but it can stay at the surface of the water? Well, this hydrogen bond explains that as well. So let's do it in the next figure. Here is the surface of the water, and I will make a small dent. I will make a small dent because I will say, let's assume over here is a leg of an insect. So again, here is air, here is water. So an insect landed on the surface of the water, and this insect has mass, so that means it has weight. I'm not going to go into equations, but you know that weight is mg. Mass of this insect times g, 9.81 meters per second square. So this weight is pulling down, and that's why the water surface is bent. But remember from the figure that I just erased that the surface layer of molecules in the water is connected to hydrogen bond, and that bond is like a membrane. So there are two molecules, let's say over here and over here, and they are further apart because remember, this was their configuration when there was no insect. Maybe this was the distance, and that distance was through hydrogen bond. But now this insect landed on the water, pushed it down, so the separation between these molecules is larger. Well, this hydrogen bond is attractive. So if I separated these molecules, the hydrogen bond tries to bring them together. Well, tries to bring them together means there is force. Let me use another color. There is force in this direction. And there is here force in this direction trying to establish flat surface of the water. Because here molecules are not affected. Molecules are at a smaller distance, and then they increase distance over here, so those molecules are attracted back here in a force like this. But now look at the beauty. This force has horizontal component and has this vertical component. This vertical component of the force is surface tension. Of course, this one over here also has horizontal component of the force and has vertical component of the force. And these two together contribute to surface tension. So, when is this insect going to float? Well, if this surface tension, vertical component of this force that results from the stretching and attractive forces of hydrogen bond, if that vertical component of the force is larger than the weight of the insect. So we would say if surface tension is larger or equal in principle than weight of this insect or weight of this object, then the object will float. So now it's clear when a man stands on a surface of the water, well, that man has huge weight that indeed is larger than the surface tension of the water or attractive force of hydrogen bond in the vertical direction, and the person will not be able to stand on the surface of the water. But if the object is light, then it is possible that that object will stay on the surface of the water. So why water has this surface tension? It's all about attractive forces of hydrogen bond that tend to recover the flat surface of the water that was deformed by stretching the surface through the weight of this object. Let's examine some other interesting property of the water. Water has very high heat capacity. Heat capacity is the amount of heat a substance needs to absorb to increase temperature for 1 degree Celsius or 1 Kelvin. In case of water, it's a lot of heat. It's 4,184 joules per gram of water. That's 1 calorie. And why so much heat is needed to increase temperature of water? Well, temperature is jiggling of molecules that are making substance, water in this case. So in many cases, or rather many substances, when they absorb heat, all of that heat, or most of it, goes to increasing jiggling, increasing temperature. But water is characterized by hydrogen bond. So when that heat is absorbed, while some of it goes to increase jiggling, thermal jiggling of molecules, some of it is also used to destroy hydrogen bonds. So not all can go into increasing temperature. And because these hydrogen bonds are strong, as I discussed, for example, in the case of surface tension, you saw it, a lot of heat is spent destroying those bonds rather than increasing temperature of water. And that's why water has high heat capacity, and that's why water is excellent coolant. Water is used as coolant in thermonuclear reactors and in many other fields of industry. Let's also explain why water is so excellent solvent. Consider kitchen salt, sodium chloride. This molecule is formed through ionic bond where this sodium gives 1 electron to chloride and it becomes positively charged and chloride becomes negatively charged. Well, you also know from this video that H2O, water, is dipole where the side of the molecule where hydrogen is positive and this side of the molecule is negative. So what will happen is, consider this to be sodium chloride, kitchen salt. So this part of the molecule over here is clearly positively charged and this one is negatively charged. Well, what will happen is that these water molecules, so if this is in water, will arrange itself so that this positive part of the molecule over here is attracting oxygens of H2O. So we will have oxygens over here because they are negatively charged in H2O, And this negative part of the sodium chloride will attract hydrogens of water molecule. But what will happen is that, remember, throughout this video we said that these water molecules here, now of course what I'm saying is that this hydrogen has some oxygen over here, this one has also some oxygen over here, and so on. I'm not going to spend time here. Similarly here, there is of course hydrogen atoms attached to these oxygens. What I'm trying to say that each of these molecules of water and these molecules of water will also be pulled in other directions through hydrogen bond, because there are other molecules of water over here. There are other molecules of water over here attracting these molecules. And there are other molecules of water over here attracting these molecules. So in other words, they will pull apart this sodium chloride. Because hydrogen is attached to chloride and everything is pulled apart in this direction by hydrogen bond, and oxygen is attached to sodium and everything is pulled apart in this direction to hydrogen bonds, then this this molecule will be split and the water will dissolve salt. Why? Again, thanks to unique property of hydrogen bond. And similar arguments hold if you take another salt that dissolves very well in water. We learned in this video about many special properties of water, and you saw they all boil down to unique hydrogen bond. We will, in this chapter 4 of Fundamental playlist, explore water. So make sure to stay tuned. Please like and subscribe, share this video with your friends and enemies and family. And until next video, goodbye.